Let's see this example and try to understand what else will be taken place. Now this is the example that we will see today. This is a new example. So here in this particular example, what is going to happen? Now it says that child copy page table, that we know that child will be copied the page table. So here in this example, we see that the parent page table will be copied in the child page table. So that we know. Now what happened in that particular program? Let's see and try to understand. Now you assume that this is a process, let's say parent process, which is executing right now. And the value of I is initialized to 23. And there is a variable taken, which is PID, is a variable. Now in this PID, the fork will return the value. So the fork will return the value in this PID as the child PID, right? Once the fork will be executing, definitely it will return some value to PID. So you assume that the child ID, the child process ID is 25. That will be returned into PID. Once this fork will be called, at that particular time, child process is going to run. So let's say you assume that this is your child process. And here also we have PID because the variable will be copied. So here also I will be there, PID will be there for child, and I will be there and PID will be for the parent. Now here, what fork is going to return for the children? It is going to return 0 to the children or the child. Now, you don't assume that the PID of the child is 0. No. PID of the child is 25, but PID of parent will be also there something. Let's say the PID of or the process ID of the parent is, you assume that this is 10, and the process ID of the child, I am assuming that it is 25. So that 25 will be allocated by the fork to the variable PID of the parent, and 0 will be allotted to the PID variable of the child. I think it is clear. Now this is the example. So both are running parallelly right now, okay? So we assume that parent is running right now. So if parent is running, it says that PID is greater than 0. So definitely 25 is greater than 0. So this part will be taken by the parent and it will be executing. Now it says that sleep 1 means it says that parent, you should go to the sleep mode. So now parent is going to the sleep mode. Meanwhile, let's say, because both are executing concurrently, so meanwhile, let's say child is also executing. So if child is executing it, it is not executing this part because this is not going to satisfy. So it is going to the else part and this is going to satisfy. And what it is going to print? It is going to print child. And what is the value that is going to print? I. What is the value of I? Is 23. Got it? Now let's say if sleep will be done. Let's say the sleep is for, let's say, 1 millisecond. Okay? Or one second or 1 minute, whatever you can say. If let's say it is 1 millisecond, on that particular 1 millisecond, child process has done its execution and printed the value. Now parent has been woke up, and it is going to print parent and the value of I. What is the value of I right now? Is 23. Done. This is done. Then it will go to the wait state. Then it is if the parent will go to the wait state, definitely it will be looking for the process. Which process? Child process to be terminated. So that part we'll see later on, because here we need exit. Here we need a code exit, which is not there in this particular program. This particular program is just to tell you about the page table, that how the page table will take place. So you know that this will be done. Now go to this example. Okay. Now this example is the same, means let's assume that the P is there and here it is executing, and then there is a fork, and fork will give the value to the PID for parent and PID for child. PID for parent is 25, PID for child it is 0. Now this particular part is going to execute by the parent. Now it will go to the sleep. Meanwhile, let's say child has been coming and it is increasing the value to I equal to I plus 1. So it is doing from 23 to 24 and it is going to print. So child is going to print 24. Now after some time, let's say parent has woke up and it is going to print parent and the value of I. So could you tell me what is the value of I that is going to print, whether it is 24 or 23? So here in this particular case, it is 23. If you have understood. If you haven't understood, see, this particular program will be copied to parent and the same program will be copied to the child, right? So child is modified in that particular program of the child only. But here I is looking for the parent program. So in the parent program, it is 23 only. But in the child program, the I has been changed to 24. So that's why child is going to print 24 and parent is going to print 23. But here we understood that because we say that the child and parent will be copied, is going to copy the page table of each other. So how this particular thing happened? Let's see the example, how this thing happened. So you see what happened here. This particular technique by which both the parent and child got the different I, this particular concept is called copy on write. Cow is a concept behind that. All parent pages initially marked as shared. That we know that all parent pages initially marked as shared. So you can see in this particular example, all are shared. You can see here, the parent is also pointing to the same location where child is pointing. Here also parent is pointing to the same location where child is pointing. Now, if you talk about this particular variable, so that particular variable is in the text part. So let's say this is the text part. This is the global and the static variable part. This is, let's say, the heap part, and this is the stack part. If this is the text part, so here we'll have I. If I is there, the value of previous value of I is 23. Now after that, what will happen is this will be done when data in any of the shared page changes. What? Data. So child has changes the data in the shared part. So what operating system will do? Operating system intercept and make a copy of the page. So in the next line, what is going to happen is it will make a separate page for the child. So you can see here, if a child is doing the modification, so it will make the another page allocate for that particular child. If parent is modifying, then also it will make a separate copy of the child for the child. Okay, so definitely it is going to make a separate copy of it. Now here you can see that because this is the copy of the child, this is the copy of the parent. That's why, because the children or the child has done modification from 23 to 24, here the I value is 24. Here, here the previous value has been taken, that is 20, right? So when data in any of the shared page in the previous example, any of the shared page has been changed, so operating system interpret and make a copy of the page like this. Thus, parent and the child will have different copy of this page. This page means only that page only where the modification will be done. All other pages will be the same. Getting it? All other pages, see this page and this page, both are having same value, same allocating to the same pages. All other pages remain the same. This is called cow. Copy on write. We'll see about the cow in the later section of the lecture also. Now let's see how we are executing a new program. Means how we are making the process. Executing a new program means making the process. So how we are making the process? So to making a process, it is a two-step process. To making a new program is new program. What is the meaning of new program? New programming is making a process. To making a process, we have two steps. What is the first step? First step is calling the fork. Another step is calling the exec system call. So fork system call and access system call. So both system call will be used. So first we'll call the fork and then we'll call the access. Now this access system call. Now let's see this example and try to understand how these two system call is going to work here. Now initially we have a variable PID, and then there is a line where we have a fork system call. So by taking this, the fork is going to be called. So once the fork is going to be called, now here this PID, the value of PID will be given the child process. Let's say you assume that 25 is the child process ID. This is for the parent. And we have the PID, which is 0, which is for the child. Got it? So now, after that, what it is saying that if PID is greater than 0, then PID equal to wait. What we have to do? So this is for the parent. Parent is going to execute and it will go to the wait state. So you see, parent, the fork system call will be there. Once the fork system call will be called, the parent will go to the wait state. And the child, what child will do? Child will call the access system call. Here we have the variation of the access system call, which is called access IP. We have access VP, we have access P. So there are a different type of around 7 variation of access system call, which will be called. This system call is for executing a program. So this is, we are calling a executable program of C. So we know how we can run a C program. ./a.out. So we are going to run a C program there. So it is looking for the C program here. So what child will do is child will call access system call. And after executing this particular program, it will call the exit. This exit will actually go for the wait to resume the parent. Okay. This is how actually a new program will be created in UNIX operating system. So what that exe system call will do is find out hard disk, the location of the a.out executable, load on demand the page required to execute a.out. So here it is called on demand. Now this access is going to look for this particular program and take the program from the hard disk to the main memory and put into a separate page, and the page table will be modified for the the child also, because it is a separate page, right? It is a new page which is not there in the parent, it is there in the child, so definitely it will be modified. So have you understood this part? So if you have understood this part, then we'll go to the other part of the program and try to see what happened actually. So first we'll call the fork system call. So in the fork system call, both parent and child will have the same pages which are allocated. Whatever the pages there, frame pages will be there with the parent, same frame pages will be there with the child. Now once the exec or the access system call will be called, then what will happen? Then would be load block from the hard disk into the page frame on demand. So it will load the block of that particular program into the main memory on demand. Then another pages will be allocated to the children. So this is C, this is the new page that will be allocated to the children as a block. So maybe in one block, it is not going to accommodate the program. So it is allocated to new page frame for the new program, which is invoked by the child process. Okay, that's why the child page table is going to modify. Parent page table is not going to modify because parent has not called the access system call. Child has called the access system. The child page table would be updated as required because now it has to be updated. Getting it? And other pages where there is no modification will be pointing to the same. It is pointing to the same page. Now let's see the advantages of cow. It is not wow, it should be cow. Okay, we can do the modification right. So in this, we have seen that what is the cow? Copy on write. So whenever in the child there is some modification or in the parent there is some modification in the shared page, then children will get a new page for the children copy. Here also the same will be done. Let's say we have, this is the parent process space, this is the child process space, means the virtual memory space, this is the physical memory space. So you see with the color that these processes are given the page table, this is also coming through the page table. But here, because of some of the processes, there are some modification that will be done. Now, there are some parts which are same. So you see that there are some parts. So this is the part of the child and this is the part of the parent which are using the same memory space. So there might be the process in the child and in the parent, both are using the same function. So if both are using the same function, it is not advised to make a separate page for that. Okay, so they are both are using the same page for that particular. So there might be same functions which will be used by both child and the parent. Let's see the process tree in the Unix Linux operating system or the Unix operating system. Now in this particular example, if you see what is in this particular example tells you about the process tree. Now in the Linux operating system, init is a function or init is a process which is a super parent process. Super parent process means this is the process which is being loaded into the main memory by the operating system. So this is the initial process, and then after fork will be used and different child process will be created. So there is SSHD process, uh, K threaded. Then there is a login page. Login is calling bash. Then there is a bash is calling PS and EMAS. And then there are different processes. You can see that process ID is also associated with all the processes. And the process ID given to the super process will be 1. So in the previous class, we have seen about the super process, and the process ID that we allowed to the super process is 1. And this super process is responsible to create other processes into the system. In the Linux operating system, in the terminal, when we write this command, ps3, it will give you the tree of the process that has been created till now. Let's see this init process, what is inside this init. Okay, that we'll see here. This is the program for init. Now you see here this particular part, there is a for loop, and this for loop is going to be infinite. So it is an infinite for loop. In this for loop, we have a fork system call, right? So when we use fork system call, definitely it will create a child process, and the fork will provide child process ID to the parent and 0 to the child. So definitely PID is less than 0. It means that fork failed. Means some negative value will be there. If fork is giving some negative value, means fork has been failed to create a child. Now if PID equal to 0 means if child is executing this particular program, so what child will do? See, child is calling the shell. So yesterday I told you about it. Shell will be called by the child, and it will be exit, and when exiting, it will call the parent. So in that way, and this particular process is running infinitely, because we know that this is the super process or super parent. Init is the super parent in Linux or Unix operating system. So you might understand that how this fork and access system call is going to work, and it is very much useful. Now let's talk about process termination, that once a process will be created, so how it will be terminated. So the first is it will use exit system call. Who will use exit system call? Definitely child will use exit system call. Now in this particular example, because that part will be used by the child, so child is using the exec to create a process, new process, and right now it is using the exit system call. This exit system call will be uh, for terminating the child and giving the control to the parent, because it is in the waiting state. It is giving the control to the parent, and then parent will be executing, and then it is what it is executing itself, and it is going out, and then another parent will be called, another parent, and that way whole child will be terminated and the parent is also terminated after that. So exit will be called by the child process, result in the process terminating. What is the result? Process termination. uh, the returns status will be 0 here, is passed on to the parent. This is voluntarily retirement. Okay, voluntarily means the process will be terminating by itself. So voluntarily termination will be there. There are some non-voluntary termination in which we have to use a function called kill function. So in the kill function, we have to put the process ID, that process we want to kill or we want to delete from the system. So that process ID we have to put, and we have to put the signal. So what is the signal? Signal can be sent to another process by the operating system. This signal will be useful to send it to other process. So the signal that the process need to be killed, that is, there are different signal that is going to apply here. We doesn't have to look for all the signal, but this is the syntax of a kill system call, which is going to kill a process by its process ID. Now, another way of killing the function is the wait. So wait will be used in the parent. So exit will be used in the child and wait will be used by the parent. After executing wait, what parent will do? Parent will go to the block state, that we all know, right? Until one of its children exit. So one of its children, if it is exiting, till now, the parent will go to the block state. If no children executing, then -1 will be written here, where the wait way is going to return -1. If children will be executing, then wait is going to return 0. Then after that, next time it is going to the else part. Who? Parent will go to the X part and call the exit. And then see, if we have a parent which is creating a child 1, since child 1 is again creating child 2. So what will happen here is child 2 is calling the exiting and giving the access to the wait of the C1. Then C1 will calling the exiting, given it to the parent. And parent, maybe the super parent is there. So it is also exiting because of this, because it will become 0. The PID will become 0. So it will be exiting and giving the control to the super process. This is how it works. Return status of the child can be collected by the wait and % status. Right now the status of this, here it is 0, but status also we can send. So the wait here, it is not taking anything, but here can take some status also. Like we have different status of a child that we'll see just now. So the process termination will be done. Some operating system do not allow child to exit if its parent has been terminated. Let's say a child is running and a parent is terminated. So some operating system do not allow child to exit. Why? Because its parent is already not there. It's not there on that. If the process terminate, then all its children must also be terminated. Let's say if process is terminating, means the parent process is terminating, then its child process also should be terminated. That termination is called cascading termination. Means all children, grandchildren, etc. will be terminated if a parent will be terminated. The termination is initialized by the operating system. The parent process may wait for termination of the child process by using wait system call, right? So wait system call is used for the parent process to wait for other child process to terminate. The call return status information and the PID of the terminated process. The status will be there, and there is a wait. So wait will be returning either 0 or -1. If no parent waiting did not invoke wait, then what will happen is the process will become a zombie. If parent terminated without invoking wait, then that is called orphan. Who will call zombie and who will call orphan? Child process. So the child process, if no parent waiting, means parent is already terminated. So that particular child process will become is invoked and the process will become zombie. And if parent terminated, okay, if no parent waiting did not invoke the wait, okay, if the parent terminated without invoking wait, then it is called orphan. Let's see these two things one by one. So what is zombie? When the process terminates, it become the zombie. Whenever a process terminate, it will become zombie. Let's say the child process is using the exit system call, it will become zombie. Or it is called defunct process. PCB or the process control block in operating system still exists even though program is no longer executing. So it is all about the child process, right? If child is executing exit system call, so the child will become zombie. So that the parent process can read the child exit status while waiting. So exit will give you the status as zombie. So once a child will become the zombie, the wait is going to return 0. When parent read status, zombie entry removed from the operating system, then process read means the process which are there, the child process will be terminated. Suppose parent doesn't read the status, then zombie continue in an existing infinite loop. That is called a resource leakage. They are typically found by the reaper process. So what operating system will do is it will run the reaper process for, let's say, for every 1 minute, 2 minute, or 3 minute of time. The reaper process will see all the zombie process. If it will find any of the zombie process, it will just rip it. Rip it means it will take away that particular process and it will kill it. Now let's talk about orphan process. Let's say we have this particular tree and here this is the child process and this is the parent process of that particular child. If let's say child is running but parent is terminated, so what will happen? This child will become orphan. Getting it? If parent has been terminated but child is running, so that child will become orphan. That orphan will be adopted by the super parent. Who is the super parent? Init is the super parent. So init will adopt that particular child. This is about orphan process. We have two type of orphan. One is unintentional orphan. Maybe parent maybe crashed. Or there are intentional orphan. Process become detached from user session and run in a background. So for the background program, which you know, there are different background program which is running. That particular background, for that particular background processes, we require the orphan processes. This orphan processes sometimes called demons, because they are running in the background and using the background services to run. That is called daemon process. The orphan which is made intentionally to run in a background, that particular process is called daemon process.